Okay, so we saw that some formulas are logically equivalent. That is, no matter what scenario is, what values are for their variables, they would have exactly the same value. We've seen a few examples. We've seen particular not A or B that was equivalent to A implies B, because the only time either of the formula can be false is when A is true and B is false. There are lots of other examples of pairs of formulas that are equivalent. For example, A and not A is equivalent to just being plain false. A if and only if B that you've seen in the knights and knaves puzzle is equivalent to it's A implies B and B implies A. That's why we write it as a double arrow. And useful fact why we find tautologies useful in addition to all the other places is that if you want to prove that two formulas are equivalent, it's enough to prove that first formula, if and only if the second one, is a tautology. So one very, very useful property of logical equivalence is that whenever you see a formula for which you have a simpler logical equivalent formula, you could just replace the first one with the second. For example, if you find A implies B confusing, as I do, because in English implication is something not very well defined, I would just replace it with not the first thing or second. A implies B is always the same as not A or B. And now I'm somewhere more understandable. I understand what not A is. I understand what or is. We could go from there. So one very common situation when you want to simplify formulas by replacing something with a logically equivalent formula is when you have negations. Our brain is not really wired to process multiple nested negations. And for us, it's not very natural to say things that are something, of not something, and not something else. For example, if I say it's sunny and cold today, and you say, no, it's not, you wouldn't really say a sentence, it's not that it's sunny and cold today. You would probably say, no, it's not sunny, or not cold. But you wouldn't really put the not in front of it. That doesn't quite sound right. So here is another example that, to me, really shows how our brain stumbles over negation of negation of negation of negation of negation. Imagine that Alice says, I refuse to vote against repealing the ban on smoking in public. Can you just immediately say by reading this sentence whether Alice likes smoking or she doesn't like it? This sentence has a whole bunch of negations piled up on top of each other. Refuse means I don't want to. Vote against, that's another negation. Repealing is another negation. The ban is another negation. So you have 4 of the no's piled on top of each other. And it's really hard to figure out what the sentence really is saying, at least to me. So whenever we see formulas that have those nested negations, we usually want to simplify them. So how do we do it? The very first rule in logic is that double negations cancel each other. We call it the law of excluded middle. In logic, if I do not disagree with you, that means I agree with you. If I write not A, that's the same as A, because not something true is the same as not something false, and not something false is true. Not something false, not true, means false. And we could use this to simplify formulas like the one that we were talking about, repealing, ban, smoking, public, by making things positive and making them a lot more readable. Let me show you some other ways of simplifying formulas with negation. Probably the most important one that you are going to see over and over in different contexts is De Morgan's laws. They are named after the British mathematician De Morgan, who also coined the term mathematical induction that we are going to see later on. And what De Morgan's laws do is, rather than having not of some big complicated formulas, they allow us to put the nots on propositions. Because saying not agree, you could just say disagree, and well, in logic, it would kind of mean the same thing. And now you're using one word and not two words. In general, you get much more simplification than that. So here are the laws. The first one says that if I have some A and B, and I want to say no, the opposite is true, it's enough for me to say that either A is not true or B is not true. So a negation of an and is an or of negations. And similarly, there is the same law for the or. A negation of an or of two things is the and of negations of the opposites. So let's just see an example. So suppose an example of using it. So suppose you have a formula not A or B. First, you would apply De Morgan's law and you get not A and not B. Doesn't save us much yet, but then you notice that you said not A, and every pair of nots can be just scratched out. So by double negation rule, it's the same as saying A and not B. So if I would say it's not true that it's not sunny or cold, it means it's sunny and not cold. Much shorter sentence, much easier to say. One useful shortcut is to apply this to negating an implication. So remember, we talked about a politician who says, if I am elected, then I will build the regional transit. When you would say, no, you didn't do what you said, is when she is elected and she didn't build the regional transit. So you could say that the formula saying that the politician didn't do what she promised is equivalent to A and not B. So let's do a few more examples. Let's go back to our it's sunny and cold today. And you say, no, it's not. So what does it mean that it's not? It could mean that it's not sunny, but still cold. It could mean that it's cold, but it's not cold, but it's still sunny. Or it can mean that it's a warm day, but it's cloudy. In all the three situations, not sunny or not cold would be true. Or here is another little bit more visual example from mathematics. Suppose you have some variable x and you're saying that x is less than 2 or x is greater than 4. And then somebody says, no, it's not for this particular variable. Then how do you interpret it? That x is both not less than 2, not greater than, and not greater than 4. So the x is between 2 and 4. So if x is not in the green part of the line, it should be in the red part of the line. So let's go back to the if-then, the confusing one. Imagine somebody saying, if I play, then I win. You could write it using the equivalence between A implies B and not A or B by either I don't play, then all bets are off, or I win. When would this be false? When saying if I play, then I win would be proven wrong. Is if you play, but don't get to win. So the negation of if I play, then I win is I play and I don't win. A negation of A implies B is A and not B. So here is a visual representation of the negation rules, already written in the form of what you do with the syntax trees when you're simplifying formulas. So the very first two things are the De Morgan's law for and for the or. The first one says if you have a piece of your syntax tree that have not and then a line pointing down to end and at the end of some two things, you don't really care which ones, you could replace this part of the tree with or going to not in both lines, and then each of the nodes goes to whatever is below that. So node of AND is OR of the two nodes. Similarly, node of OR is the AND of the two nodes. As we just did, we can shortcut and say node of A implies B is AND of the A and node B. So if you have node going down to implication, going down to two things, you replace it with AND, which goes directly down to the left thing, but goes to the node and from node to the right thing. And finally, if in your tree you find that you're going node, node, you could just erase the node, node and make a line directly to whatever formula you have. Okay, let's run through a long example of negating a formula using the syntax tree. So here are the rules. We always start from the top when we are negating, and we keep applying those modifications like we had before until we reach the actual variables. We may end up with a node in front of a variable, or we may end up with just a variable itself, but we wouldn't have double negations, and we wouldn't have nodes anywhere except for the part of the tree which is just above the very bottom. So let's try to do an example. Suppose you have a formula which is A on node B implies node A and C, and you want to negate this whole thing. Or maybe you get this whole formula negated and you want to simplify it to make it something a bit more understandable. Let's do it. So first, you start by saying it's a node of an implication, because if you draw a syntax tree for the formula inside, the implication would be on top, and then you put the node on the very top of it. Applying the rule that you've just seen, we switch that node imply to AND of the left thing and the negation of the right thing. And notice that at this point, if the only thing that we did with the formula was to add the node on top, we are done with the left part of the tree. Nothing changed except that this OR is now connects to an AND rather than connecting to the implication. But on the right part of the tree, we just introduced a node, and it's really too high up in the tree for comfort. Let's try to see if we could simplify the right side of the tree a little bit further. So we have the combination that there is a node which has an AND underneath, and by De Morgan law, we know that we could switch AND goes on top and node goes on the bottom, and there become two of the nodes. And also the AND switches to OR, so let's apply the De Morgan law. And so AND going to node became OR going to two nodes, and the things underneath remain unchanged. So now, on the left side of this tree, we got the situation when we have node, node. That's great because we can just erase the node, node part and bring A higher up. And finally, on the right side of the tree, we really cannot do anything else because it's node C. We cannot simplify it further. So the bottom line is we took a formula and we put the node in front of it. It got kind of cumbersome, but we made it simpler by taking the nodes all the way down until they reached the variables. And in the process, we got rid of some double negation, and we flipped some ends to ORs, ORs to ends. So just to remind you, here are the rules that we used. The first two are De Morgan laws, which say if you have node on AND, that's the same as OR of two nodes. And if you have node on OR, you have AND of the two nodes. The last one is a double negation. That's the easiest one. If you have node, node, just get rid of it. And finally, you could combine the two of them into a shortcut that node of imply is AND of the first thing and node of the second thing. So hopefully, this visual representation will make it a little bit easier to remember what those laws are doing and apply them as you are going through the syntax trees to simplify your formulas. So finally, let me finish with another puzzle. It's another puzzle about knights and knaves, where knights always lie and knights always tell the truth and knaves always lie. Here is the puzzle. You see three islanders talking to each other. Let's call them Arnold, Bob, and Charlie. You ask Arnold, are you a knight? But you cannot hear what he answers. And actually, it's a pretty useless question to ask somebody. Think about that. But then Bob pitches in. Arnold said that he's a knave. And Charlie says, nah, don't believe Bob, he's lying. There is not much you could say about Arnold in this situation. But can you figure out whether Bob is a knight or Bob is a knave, and whether Charlie is a knight or Charlie is a knave? I'll let you think about that for next time.